Hey everybody, my name is Kyle Corbitt. I work on a company called OpenPipe. Excited to be talking to all of you. This is a little bit weird. I don't know if I've ever given a talk like this sitting, but I guess for camera reasons I am. So I'll just be very dynamic with my hands maybe. I don't know. We'll see. Anyway, we're going to be talking about fine-tuning here. Specifically, we're going to be talking about whether you should be doing fine-tuning, and we'll also define what fine-tuning is. If that's unclear to anyone in the audience, don't be worried about that. I am going to start by sharing my biases. I happen to work for a company called OpenPipe that explicitly is about fine-tuning. So there will be, I have an opinion that fine-tuning is at least sometimes useful. That said, it's also important to say that most of the people who come and ask us about whether we should be fine-tuning our models versus just staying with prompting, I actually tell, you know what, at the stage and with the problems you have right now, I would not recommend you fine-tune. So the answer to this is not going to be, yes, you always need fine-tuning, as you'll see as we get into it. But let's talk about when we do. There are three main components that I would like to cover today. The first one is why. Actually, you know what? I'm going to do an audible here. We're going to add an extra component, 0. 0 is what is fine-tuning? I want to, just a raise of hands, how many people kind of would be able to describe at a very high level what fine-tuning is in the context of machine learning or LLMs? Okay, cool. So it's looking like probably less than half of the audience here, which is great. So we definitely are going to add a step 0 here, which is what is fine-tuning. Fine-tuning conceptually is really simple. Probably everyone knows that these machine learning models are trained by being exposed to vast amounts of data on the internet, sometimes from human feedback, lots of different sources. Fine-tuning is basically just a continuation of that process, where instead of continuing to train this model on vast amounts of random data that's not related to your problem, you gather specific data that is relevant to the task that you or your company, whatever you're using this model for, is trying to do, and you train the model on that specific set of data. That's what fine-tuning is. It's you're actually changing the weights of the model to understand your problem better. Okay, so that is what fine-tuning is. The next three parts of this talk are going to be, why would you do it? Prompting actually works really, really well. So is it even necessary? Do you need a model that is specific to your task? The second question is, when is the right time to do it? So if we know that under some circumstances it's useful, when do those circumstances apply to me? When should we be doing it? And then finally, we'll get into the brass tacks of how you actually go about this. So when that time comes, or for many of you, you may actually be there, you understand what the steps you need to take are. Okay, let's start with the first point there, which is why. Why do I care about fine-tuning? Why is this something that I would spend my time on? All right, I'm going to ask for another show of hands here. Who has seen a graph something like this at some point? Basically, where you're kind of measuring a model cost versus the quality or some metric of how strong that model is. Raise your hands high if you've seen a graph like this sometime before. Okay, similar, maybe there's a lot of overlap I'm feeling in the distribution of people who knew about fine-tuning and people who'd seen this graph. Maybe about half of folks had as well. So this is pretty standard. This is basically, this is one way you can decide what model you should use for your task. You can look and say, okay, there's different tokens per dollar up here, so maybe you have a hard limit based on your unit economics or how much budget you have to spend on this for how much you can, how smart a model you can do. And then that'll kind of dictate which model you choose. By the way, this is one way of graphing these. There's other dimensions you can graph these models on as well. A very common one that is relevant for many use cases where you have interactive components is you can measure the output quality versus latency as well. And so if you're doing anything with, say, voice chat, or even just normal chat, or you're doing a bunch of calls in a row in sort of an agentic framework or something, and the user's sitting there waiting for you to do all these calls, you're going to start caring a lot about latency. And that's something that's also very correlated actually with model cost, in the sense that cheaper models are usually lower latency because both of those are associated with model size. The smaller your model is, the faster it'll be and the cheaper it'll be. So moving to smaller models does have some substantial advantages. The disadvantage, of course, as we're seeing in the other axis, is generally as you get to the smaller models, you're getting less intelligence. You're getting just a model that's not as good on kind of the quality. Okay, so this is a very general trade-off, and we can actually draw on top of this chart. We can draw this nice Pareto frontier, which is okay for a given amount of money I can spend. What is the best model, right? So if I'm doing something at huge scale, I'm scraping the whole internet. Well, maybe I'm looking down at this tail end of the distribution where we've got Gemini 1.5 Flash, which is super cheap to run, but not that strong. But if I'm doing super high volume, maybe I need that. On the other hand, if I'm doing a very low volume use case, then maybe I want to just get the best quality model I possibly can. And we're going to be at the other end of this, way up with Claude 3.5 Sonnet, which is potentially the strongest model that's available publicly today. Okay, so that's kind of like very, very intuitive. That's how you make that decision. Okay, we're going to take an aside. I promise I'm going to tie this back to fine-tuning in just 1 second, but we need to kind of make another observation here. So what we're seeing right here is this is actually some research that members of our team at OpenPipe put out some time ago. It's a very simple thing. This is just a definition of a prompt chain that we have found actually can improve model performance significantly. This actually is not unique to us either. We basically were just grabbing kind of like things that were known in the ecosystem and quantifying the output. But this is just an example of a basic prompt chain. Okay, why would you do a prompt chain like this? Actually, let me talk through what the prompt chain is in case that's not clear. First of all, you're just going to call the LLM the way you would normally. You're going to ask it to generate several different responses. You will then kind of call your LLM again and say, hey, look at these outputs. Tell me what's good or bad about them. And then finally synthesize them into a final response. Okay, pretty simple. Again, this is actually a pattern that a lot of folks use. You'll see it implemented in frameworks like LangChain. Why are we talking about this? Well, the reason we're talking about this is because going through even a very simple chain like this can actually help your output quality significantly because for a number of reasons. One reason is that these models are not necessarily deterministic. They can make mistakes in like an inconsistent way. So we've got these 3 responses here. If maybe like one of them goes off the rails, then you're going to notice that, then kind of this prompt 2 will notice that and kind of account for it. Another reason is just giving it more time to think, giving it more time to reason over the thing can help it improve its quality. So in practice, what we find is that this does, on average, help performance. Okay, there's some downsides though here. It's slower because remember we're calling our LLM 3 different times with 3 different pieces of information compared to just like a single call. It's more expensive. Again, those 3 calls, it's going to cost at least 3 times as much. And of course, on the other hand, on the positive side, you are on average going to get higher quality completions. And we actually, on our team, we validated this. We actually have the top entry right now on both the Alpaca eval and Chatbot Arena hard auto benchmarks right now using literally exactly this technique. So the quality is there, but again, it's slow and expensive. Okay, so what does this do? Let's say we're bringing that technique into this output quality versus tokens per dollar thing. Well, we can actually add that prompt chain we were just talking about as sort of its own category here. And I'll put that right there, okay? So we're calling that mixture of agents. That's just the name of this specific prompt chain. And this mixture of agents approach, let's look at kind of where this is on the graph, right? And again, we'll see exactly these trade-offs. So it's way over here on the left. That means it's way more expensive than anything else we've got here. And it's also slower than anything else because, again, that's correlated. On the other hand, it is the highest quality outputs we can get relative to just calling these prompt models, these base models. Okay, so this is interesting, right? This is, what the cool kids are calling like, increasing inference time compute, basically like doing more calls at the, at inference time to get higher quality. That's a really useful tool to have. Of course, it does come with those downsides we said, which is this is now much more expensive and slower. And we've actually found for a lot of use cases, this gets too expensive and too slow. I mean, have it take 3 times as long, having it, cost 3 times as much, puts this out of the range of many actual like real production use cases. But we're finally, we're getting to the climax here. I hope everyone's excited because I'm about to show something that's like really magical, okay? Okay, it's not going to look magical. I will explain why it is magical. All right, look. Is everyone saying ooh and ah? Okay, thank you. Yes. Fine, I will explain why this is magical. Okay, so what we have found is that there's a really nice pattern you can do, which is you start with this mixture of agents approach. Okay, you get the highest quality completions you can. And maybe that's too slow, maybe that's too expensive to use in production, that's fine. You can do this kind of offline, you can use one of these other models in production and then use this mixture of agents to sort of like reprocess your data later. Once you've done that, if you take the outputs, those very high quality outputs you got, and you just fine tune one of these other, say these open source or even there's closed source models, either way it works, models on those very high quality outputs, you end up with a model that for your specific task, and this is very important, you can't just do this like generally with like any set of outputs. It has to be like very specific to your task. But what we find is if you do this with inputs very specific to your task, you can actually recover and retain a large fraction of the benefits you got from that very slow, very expensive mixture of agents with a much smaller, much faster, much cheaper model through fine-tuning. So concretely what you're doing here, you're taking those outputs, and then you are training this smaller model on those outputs that were specific to your problem. And what you get out of that is you get a new version of that model, which is much better. Another way of looking at this is kind of starting from the base model. So you can see each of these fine-tuned models that's showing up in green here comes from one of these other models that we already had on the chart, right? So we've got Llama 3.170B. By the way, this is real data. Like these are plotted from actual evals that we ran internally, averaged across 4 different customer tasks with fine-tuning on their specific data sets. So this is not just an illustration. This is actually like typical results that we see. Basically, each of these base models, once it's been fine-tuned on the task, the performance improves drastically on that specific task. So this is kind of the whole trick. This is the reason you would do fine-tuning, is because let's say that you can only pay, like this much per token because you're doing a high volume task, or, you have high latency, or you need low latency. Well, by adopting fine-tuning, you can keep your costs way down here and push your quality way up here. Okay? That's the trick. That's the reason you would want to do fine-tuning, is because for a much lower cost, you can have a model that works much better on your task. And so what does this do to our Pareto frontier we have right here of the cost versus quality trade-off? Well, if we incorporate those, we can see, boom, it just moves way further out. So wherever you want to be on that frontier, however much you can spend, however much latency you can afford, you're going to get a better result if you have a fine-tuned model that is specific to your task than if you're just using a general prompted model that has to be good at your task and a million other people's tasks as well. That's the whole thing. That's the reason you would do fine-tuning. Okay, so super exciting. Look, we pushed out the Pareto frontier. So let me just, so satisfying. Okay, we pushed it out. Awesome, no trade-offs. We should all be doing fine-tuning, right? Okay, unfortunately not. There are some trade-offs. There are reasons why it doesn't make sense to just automatically do this immediately, and I want to talk through that right now. The main reason is because this process, it takes time, okay? It's going to take engineering effort. You have to put together your data set. You have to basically spend the time to figure out how to fine-tune the model, and then you have to deploy your own specific model, custom model, which is not the same one everyone else is using. There are challenges involved in just operationally in doing that. And then the second very important one is it decreases your flexibility. So these models, once you fine-tune it on your specific task, on whatever it is you're trying to do, they're going to be very good at that. But it's actually going to be worse, or at least have much less improvement, and in many cases actually worse, on a bunch of other tasks. So your model becomes less flexible. It's very good at your thing, very bad or relatively bad at everything else. And this also leads to operational challenges because, say you've got a bunch of, whatever it would, let's say you're doing, information extraction from documents. Well, now if a customer comes to you and they have a new document type that you haven't seen before that wasn't in your fine-tuning data, you may not do as good a job on that as you would have, without the fine-tuning. So you have to actually monitor for that. You have to make sure that if the inputs you're getting actually do match the same data, or the shape, the kind of data, the class of data that you had when you were actually training. So those are the two trade-offs. Those are the reasons you wouldn't want to do that. And I want to get a little bit more concrete with that on kind of how you can think through those trade-offs and make that decision. So given those trade-offs, there's obviously like you don't want to do this immediately, because when you're very early on, when you're developing either a new product or a new or you are developing like a new feature on your product, you're probably iterating really fast, and this flexibility thing right here is at a very high premium, and time is probably at a high premium as well if you're trying to get to market quickly. So it doesn't make sense to do it immediately. When does it make sense? When should you invest the time in doing this? The answer is when your prompted workflow runs into one of three barriers that you cannot fix with prompting. And those three barriers that we see, and this is in rough order of how commonly we see them, is first, if it's too unreliable. If you find that maybe 85, 88% of the time, your model is doing what you want it to do, but then, that last 12, 15% of the time, it's not. And you've tried prompting techniques, you've tried like training, basically like all the stuff, few shot examples, and it's just like not quite able to get there all the time. Fine tuning can be a huge benefit. It can get you from that, say, 85% up to maybe like a 98, 99% accuracy, and that can make a big difference in your user experience for your users. The next one is too expensive. So as we saw, you can move from like a Claude 3.5 Sonnet down to like a Llama 3.1 8B, which is like 1.5 orders of magnitude cheaper, with actually similar or superior performance. And for many use cases, that can be really important. Or too slow. Again, moving to those smaller models gets your latency down. So if you don't run into these issues, if you're totally happy with quality and the cost is not, your unit costs don't matter that much, and latency is fine, you probably shouldn't fine tune, because these are the problems it helps with, and if you don't have the problems, you shouldn't solve it. But if you do run into them, then that's when it makes a lot of sense. What we often find is this makes sense as you're starting to scale, as you're getting more, you're going to have more volume, you are going to have more usage, unreliability is going to be more annoying because it'll be users you don't know, and you're just going to have to be spending more money. And so often it's when you're actually scaling, that's when we see these issues start to becoming more acute. Very commonly. Okay, so I don't have that many minutes left. We're going to do a lightning round of how do we actually do this. And what I'm hoping you come out of this part with is this is actually not that hard. Okay, we've had customers successfully deploy fine-tune models with less than an hour of engineering time, literally going from GPT-4 to having their own fine-tune model deployed. So hopefully that's where we come out of here. Okay, there's 4 steps here. You got to prepare the data, you've got to train your model, you have to do evaluations, and finally you have to deploy your model somewhere. All right, these are the 4 steps. We're going to go through them. Does anyone here have experience with sort of traditional pre-LLM machine learning? I'm just curious. I realize that's not the main audience. Okay, we do actually have a larger number than I expected. Okay, awesome. Well then, those of you that do have that experience, if you've gone through this process before, are going to be very familiar with this nice acronym I've come up with to explain these steps. This was actually a really hard process. Like this is, when you hear people say don't fine tune, it's often because they have that PTSD from traditional machine learning, where this would typically take at a minimum weeks, very often months to go through the process. Typically it's actually the data preparation and then evaluation that take a lot of time. We're going to talk through how to make that much faster and why this is different now. Okay, preparing data, extremely simple now. The reason why, you can start with those prompted models and you can just start gathering data from there. If you can get one of those mixture of agents flows working, for example, you can deploy that in production, just capture all the requests and responses and train on that, and you can be in really good shape. Okay. Now, sometimes even those mixture of agents outputs are not strong enough. There's a lot of, basically, sometimes you do have to do a little bit of data management. There's lots of tools out there. There's open source tools you can use to basically like quickly review your data set. And you don't need huge data sets for this to work, by the way. In sort of this LLM regime era, a few hundred examples is often plenty. And so having a human manually review those is not insurmountable. You can also use LLMs, different types of filtering. I do find that third parties like Scale AI are probably not a good fit at this stage for most people, just because LLMs are able to replicate them. But internal human review can often still be really valuable because you have unique insights into what you're trying to accomplish. Okay, next you need to train the model. This part is relatively simple for anyone who has like a strong background in software engineering. Like if you can, if you can even prompt a model, you probably actually, and you have that last step, the data set, you can train it. We make this really easy at OpenPipe. There's other hosted providers like Together, Fireworks, Anyscale. There's open source libraries. In fact, of these three, I would really highlight Unsloth as doing a great job on the kind of like being approachable and user education point of view. They've got great notebooks like that you can see just how to do it. They have great code examples. So this process is actually not that hard. There's good guides out there. You can find them, on Medium, other places. And of course, the hosted providers make it very easy as well. And then you need to evaluate. I'm running a little low on time, so I'm going to speed through this a little bit. This could be like a whole talk. This could be a whole conference just on evaluations. The way I think about it, you need two kinds of evaluations. You want some kind of inner loop evaluation that you can run really fast. We find like using an LLM itself to judge the outputs of your fine-tuned model is one example of this. If you're doing, say, classification or information extraction, sometimes you can have a golden data set that you compare to. And then you also want an outer loop of evaluations. And this is like, okay, what is the actual business impact I am trying to use this model for? What is the actual higher level goal? How do I measure if it's doing that or not? That's going to be very, very specific, of course, to your task, and typically requires actually running this in production and seeing what outcomes you get. But usually you do that once you're happy on this, the fast evals that it seems like things are mostly working. Okay, and then finally you need to deploy it. There's at this point, the ecosystem is actually quite mature here. Of course, we do this at OpenPipe. There's lots of different hosting providers for inference that you can just upload your weights to, and they'll take it from there and give you a nice endpoint. Sometimes they'll even do auto scaling for you. We do that. And you can also run it yourself. So you can run with VLM. There's actually, you can even run it on CPU, like with llama.cpp and Olama, tools like that. So this ecosystem is actually quite mature at this point, and there's lots of good guides out there. Okay, so that's it. I've got 4 minutes left, and anyway, this is kind of just to go back to the why. The reason why is you get much better quality at a given point. And that's it. So yeah, happy to take questions. The outputs we use, so this is somewhat task dependent. That said, we have found that like these very basic prompt chains, like the mixture of agents that I mentioned, are actually pretty general. And so for like 80% of our users, they can just apply that and relabel using that, and then they get good quality. You asked about some like very technical specifics, like which layers do we freeze and unfreeze. So with OpenPipe specifically, basically you have full flexibility here if you're doing this with open source. With OpenPipe specifically, we will target all of the linear layers, and we do what's called a LoRa fine tuning. So basically we freeze all of the layers, and then we insert our own adapters on top of all of the linear layers within the model, which are much lower rank. They're relatively small matrices, and we tune those. This is a fairly well understood industry technique. The advantage of doing it that way, as opposed to training all of the weights, is mostly at deployment time. You end up with basically much more efficient deployment. So instead of having to like slug around these, 16 plus gigabyte artifacts, which are like the full weights, we just have these very small, like 40 megabyte adapters, which means we can run them really fast, have 12 of them loaded on the GPU at the same time, running batches in parallel with 12 different models, and then swap them in and out in fractions of a second. All of that said, one thing I would emphasize is that we have done a lot of different studies and ablations on the actual fine-tuning techniques. We have found that for 90% of use cases, the differences are very marginal. Even switching different base models, the differences are relatively marginal as long as you stick with kind of some of the higher quality ones. What makes all the difference in the world is the data quality. Like honestly, that makes a huge difference, and most other things, frankly, mostly don't. I think, so this definitely does start getting to use case specifics. I would say in general, the pattern we see is the opposite. To generate the initial data and filter your initial data, you really want to go for the largest model you can afford, because all else being equal, it's going to be stronger. And then you distill that down as part of the training into the smallest model that can get you the results that you need. I don't think there's much advantage to trying to minimize the size of the model for sort of the initial data generation and filtering. Yeah, because currently Anthropic does not allow you to fine-tune Cloud 3.5 Sonnet publicly. Otherwise, yes, we absolutely would. What makes it faster is moving to a smaller model. So even without fine-tuning, like Llama 3.18b is already much faster than GPT-4 Turbo, just inherently. The problem is you're trading off quality. So what it does is it lets you, for a given model size, get higher quality, and then you can trade off some of that quality basically by moving to a smaller model size because you're able to recover so much through fine-tuning, if that makes sense. You mentioned RAG as another technique. RAG is basically pulling relevant context into your context window, like at the time you're running inference. We find that for the purposes of gaining new information, RAG makes a ton of sense. And it can also work to some degree as a way of pulling in context examples of doing the task. It's not as good at basically teaching the model the shape of its output or the feel of its output, the type of tone it should use, the type of words it should use. Those kind of things don't really come well through RAG. But as far as the specific information it should use in generating an output, you can use RAG for that. So in practice, we find a lot of people use them in a complementary way. They'll use both because they help with different aspects.